Hey guys, and welcome back to how to make elements from household materials. And today's element is going to be tin. Now, tin is not actually used in tin cans anymore, as one might think based on the name, and it's not really found in very many uses in its elemental form, at least not nowadays anymore. Tin foil is also made of aluminum, not tin. But some of the uses that tin does have is in LCD screens and stuff. There's a compound called indium tin oxide, a very thin coating on there, but that's not very much. The only really reasonable source of tin that you're going to find today, that I can think of at least, is going to be tin solder. Now, this solder contains both lead and tin, and possibly traces of silver, and has a very low melting point, as both tin and lead do, and it's used to make electrical connections and stuff, especially this fine solder, because you can also get pipe solder, which will work just as well. But this fine solder, as does finer, will hopefully dissolve faster. The one downside to electrical solder, and possibly some types of pipe solder, is that there's a flux on it so that it sticks, flows a bit easier, and that's found on the there's actually a core of the flux on the inside of here, and the little spool here does say rosin core. Nonetheless, I'm hoping that's not going to affect our reaction too much, but after doing a lot of digging and stuff, it turns out that, tin and lead are not easy things to separate. Hence why I don't think anyone has actually done it on YouTube, at least. Lead will dissolve in things like nitric acid, whereas tin won't, because it'll form the oxide and then passivate it, so no more will dissolve and stuff, and it's just a whole big mess. And there's not a lot of information on a huge amount of tin compounds, at least not online, through Wikipedia or anything. So I used my Merck Index, which is a big dictionary of a huge amount of chemicals, and it basically tells you everything about that specific chemical. It's extremely useful. And I looked up some tin compounds, and turns out that stannous acetate, tin acetate, can be produced by reacting tin metal with glacial acetic acid. So that's just high purity acetic acid with very little water in it, and we actually made some of that in a previous video, and we have it right here. And if you're wondering, acetic acid is just vinegar. But you do definitely need some very concentrated stuff, which can be easily made from household materials. Anyhow, so the tin will dissolve in the glacial acetic acid to form stannous acetate, which is water soluble. And then the lead will actually dissolve in acetic acid in the presence of concentrated hydrogen peroxide to form lead acetate, which is also water soluble. All acetate salts are water soluble except for silver acetate. Nonetheless, so what we're going to have to do is make a solution with our glacial acetic acid and hydrogen peroxide. What the hydrogen peroxide should do is it should first oxidize our lead to lead oxide, which will then immediately react with the glacial acetic acid to form our lead acetate. Now, we have to be very, very careful because lead acetate is very, very poisonous, and glacial acetic acid can cause severe burns to your skin, your eyes, and your respiratory tract. Same with hydrogen peroxide. This is 35% concentrated here, and very powerful. This I purchased in Korea because you can buy 500 milliliters of it for 50 cents in Korea at any drugstore. It's extremely cheap. If you're looking to buy it in Canada, you can go to some health food stores. I found this in Canada, 29% food grade hydrogen peroxide, and that will work just as well. But for this particular experiment, I'll be using this 35% concentration. Anyhow, so to begin, I think we'll probably measure out about 75 milliliters of glacial acetic acid into this Erlenmeyer flask here. We'll chop up several grams of this tin solder here, and add, let's say, 15 milliliters of this 35% hydrogen peroxide. I actually don't know really anything about this reaction, we're just guessing here, because there's not much information on the dissolution of lead and tin. So we're going to be trying this, we'll see if it works, hopefully it does work. After that, we'll work on separating the lead compound from the tin compounds after they're in solution. So, I'll weigh out those things and measure everything out and add it to this Erlenmeyer flask. And then of course we're going to be refluxing outside. Now make sure, when you open up your glacial acetic acid, that your fume hood is on, or that you do it outside, as it is very, very potent and really does hurt your nose. Anyhow, I'll get everything ready, and then I'll meet you back. Okay, so I'm heating this up outside, and after adding the hydrogen peroxide and heating, it didn't look like a whole lot happened. I think a bit dissolved because the tin lead alloy became a bit shinier, but nothing really happened. So then I thought, concentrated nitric acid. We made this in a previous video, and this is fuming nitric acid, very, very highly concentrated, above 90%. Anyhow, and that would actually react with the lead to hopefully form lead nitrate. I tested before, it didn't react with the acetic acid, and I was hoping that it would help react with tin oxide produced, or like the acetic acid, because when the tin reacts with the nitric acid, it will produce tin oxide, which will hopefully react with the acetic acid to form our tin acetate. So in this way, I was hoping it would go into solution. And you can see the brownish color of nitrogen dioxide gas as the nitric acid is decomposing. We're just refluxing this acid mixture. And I added 10 milliliters of this 95% nitric acid here. And it seems to be going very well and everything. We're just slowly refluxing it, and hopefully everything's dissolving. It looks like it's dissolving, so this is a good sign. So let this hopefully finish up, and then I'll meet you back. Okay, so it's been refluxing for over an hour now, and from the looks of it, and when I lifted it up a bit and swirled it around, there's no more solid lead pieces in here. Everything has been more or less dissolved. Now the white color is most likely tin oxide, and any lead oxide that was produced should have hopefully reacted with the acetic acid to produce lead acetate. Or it could also have reacted with the nitric acid to produce lead nitrate. I'm not totally sure what all reaction has gone on here, because we have hydrogen peroxide, which is actually probably all decomposed by now, and we had acetic acid and nitric acid all in here. But the tin oxide looks like it's not reacting with acetic acid, and it could be the nitric acid that's preventing this. Not totally sure why that would be happening, but possibly. But it doesn't look like any more dissolving's happening or anything. So, now that everything's reflux like this for so long, and it appears that all the lead and tin from the solder is dissolved, I think I'll cool this down, and then vacuum filter it. And by vacuum filtering it, we should be able to separate off whatever white compound this appears to be. That should be the tin oxide, which we can then react with, hopefully, hydrochloric acid to form tin chloride, and then we can get our tin metal from there. And then, of course, the rest of the solution will need to be dealt with, because it contains toxic levels of lead in it. And lead is really highly toxic, especially lead nitrate, as it will be absorbed through your skin. It can cause lead poisoning. So gloves must be worn, a solution of sodium bicarbonate, which is baking soda, must be kept nearby when dealing with this, and you have to wear eyewear, and just be really, really careful, and definitely don't dump any of this outside. Sodium bicarbonate will actually react with lead compounds to form lead bicarbonate, which is extremely insoluble, and thus it's not as much of a hazard. So if you get it on your hands, immediately dunk them in a sodium bicarbonate solution, so that, say, lead nitrate will react from lead bicarbonate, which won't cause nearly as much harm to you. Then wash your hands lots. Anyhow, that's basically some of the safety things with lead compounds. So I'll let this cool, I'll vacuum filter it, and I'll make sure to have gloves and all the safety gear on. So I'll do that, and then I'll meet you back. Okay, so what we actually did was we added another 35 grams of solder to this, because it looked like it dissolved pretty well the first time. And I let it reflux for another 2 hours, and I had to add another 10 milliliters of fuming nitric acid to finish dissolving everything. But it appears that all of the solder is dissolved, and we have a very thick precipitate of some sort of tin oxide in there, or what I think is tin oxide. It's also slightly yellow colored, and I believe lead oxide is also yellow, though theoretically this should react with either the acetic acid or the nitric acid to form a lead salt. But nonetheless, we're going to go ahead and cool this down now and filter it off. The yellow color and this orangish compound there is actually the flux that was inside of the solder, and this is just floated out. I believe most of it was oxidized by the nitric acid, but it still appears that at least some of it has not been oxidized. It could have also contributed to the overall yellow color. Nonetheless, in the purification of our tin, this will not matter a huge amount. So I'll go ahead, let this cool down, and then we'll vacuum filter the mixture. And be sure to wash it several times to remove any soluble lead nitrate or lead acetate salts, because we don't want those in our final product. And then it doesn't matter how many times we wash it, because we're actually going to be reacting with the lead solution with sodium bicarbonate. And almost all lead salts will precipitate out with sodium bicarbonate to form lead bicarbonate, which is extremely insoluble in water, and thus can be easily filtered off, separated, and then you can recover your lead from that. We definitely don't want to be dumping our soluble lead salts down the drain or outside for that matter. Anyhow, I'll filter all this off after it cools down, and I'll meet you back then. Okay, so lots of interesting stuff has happened in the past little bit. So everything was successfully filtered off, and the filtrate from our solution is right there. And I took a small little bit of it and added it into this beaker right here, and we have confirmed the presence of lead ions in solution. So clearly some lead did dissolve into solution, either as lead nitrate or lead acetate, because when we diluted that to about 75 milliliters of some water, and then added a saturated solution of sodium bicarbonate, lead bicarbonate precipitated out, as we can clearly see. And lead bicarbonate is an extremely insoluble salt of lead, so it's very, very good for determining whether or not you have lead in solution. So we clearly have lead in solution, so clearly some did dissolve into that solution, which most likely means there's some tin which might also be present. But from what was left in the filter, I transferred into this large 1 liter beaker right over here. And if we take a closer look at that, you can see that it's off-white color, but pretty white. Now, I transferred into this container here, this beaker, and diluted it with a bunch of water just to wash it, to remove any of the leftover, clearly lead-soluble salts that were in it. So I'm going to go ahead and filter this again, but it's important to note that a vacuum filtration will not, or doesn't seem to work very well for this, as it very quickly clogs up the filter and just doesn't proceed. So gravity filtration, while much slower, is far more efficient. So I would highly recommend to continue gravity filtration, but nonetheless, we'll take all of this and we'll try to filter it off again. This should hopefully contain less lead, and most of the lead should be in solution. And whenever you have a solution of lead, just add a saturated solution of sodium bicarbonate to it, an excess of it, to precipitate out any lead salts, because lead salts are highly toxic, and we definitely wouldn't want that going into the environment. Anyhow, so I'm going to do a few more tests and stuff. We'll definitely filter this, and I'll meet you back, and we'll try to separate the tin from this. Okay, so I just did something kind of interesting. So we took that filtered solution that was kind of yellow a moment ago, and we diluted it in a whole bunch of water, as you can see right here. And I was wearing gloves a moment ago. They just had stuff on them, so I took them off for the filming. Make sure you wear gloves always when you're dealing with these toxic lead solutions. Anyhow, but it was diluted, and what this is going to do is, A, leftover acetic acid, concentrated glacial acetic acid, reacts very slowly, surprisingly, with sodium bicarbonate, and B, it's fairly dense, and by diluting it like this, the acetic acid isn't dense, sorry, it's kind of viscous, but by diluting it like this, it becomes much more, well, less viscous, and because we have a larger volume, our lead salt that we precipitate will sink to the bottom, hopefully, faster. And as lead is a very heavy salt, the precipitate should fall to the bottom relatively rapidly. Anyhow, so we then mixed up a whole bunch of sodium bicarbonate solution, hopefully in excess, and we dumped it into this whole mixture here. Of course, slowly, because as it reacted with excess acetic acid, it produced lots of carbon dioxide. But that was left, and a bit of bubbling occurred, but it died down. And then you could very clearly see a white precipitate of lead bicarbonate, which is extremely insoluble in water. Anyhow, once this clears up a bit, we'll be able to add a bit more sodium bicarbonate solution, and if more precipitate forms, then we know we haven't reacted all the lead. If no more precipitate forms, then we know we've reacted all the lead. And once we've reacted all the lead out of solution, this solution should be pretty safe to dispose of, as all of our lead bicarbonate should be on the bottom. We can then take that and separate it out, and we'll use that to recover lead from. Okay, so an update on what's happening. All of our lead has pretty much fallen to the bottom there. We'll give that another half an hour to fully settle out. That only happened in probably about 10 minutes, so it does fall out very quickly. But we're going to make sure everything falls out before we decant off the upper layer. And that solution that we filtered from earlier, the one in the big tall beaker, you can see most of it's been filtering through gravity filtration, and the rest of it's in the beaker over there. And I've just placed on the hot plate because the remnants of what's in the beaker have that kind of characteristic orange color of lead 2 oxide. So I think that might be lead 2 oxide. It also fell out of solution quite quickly. So I'm thinking that it might be a lead compound, not totally sure, but we're going to heat it up, and if it also contains tin, we're going to be trying to separate that. We'll see how it all goes. This is quite iffy. You know, tin chemistry hasn't been studied a whole lot very well from what I've tried to research and stuff. Yeah, and it forms some interesting compounds, like tin reacts with sodium hydroxide from sodium stannate, not tin hydroxide or anything. So I'm not sure if displacing out a tin ion from a solution with a hydroxide would form tin hydroxide or sodium stannate. I really don't know. It's quite confusing, and tin just behaves kind of differently. We're going to try to precipitate everything out here and separate everything, but we'll see what we can do. We might have to use a solution over here to our right as our main source, as I'm pretty sure this does also, because it can definitely contain lead ions, I'm sure it contained tin ions also. But also, based on the amount of precipitate that we got on the bottom, it looks like there's not very much lead that was actually left in this here, so this precipitate here could also be tin oxide. It's kind of confusing. We'll figure everything out. Hopefully we'll be able to get some tin out of this though. So something interesting was just happening. I just turned off the heat and took it off for a moment because it was bubbling. The solid, it is now a solid. It's all been dried out and everything, but I believe it was decomposing. So all we could probably possibly have in here would be tin and lead ions. Now, based on previous knowledge, such as calcium acetate decomposes to calcium carbonate and acetone. Now, as I was heating this, I was smelling a very strong smell of acetic acid, which I was assuming was from leftover acetic acid from the reaction, but perhaps it was decomposing, because when I took this off, it was like bubbling, like a gas was escaping. I think we possibly had either lead or tin acetate. Now, I'm not totally sure what's happened here, but I think perhaps when we added the nitric acid to that reaction mixture, possibly prevented the lead or tin acetate from dissolving, or because we didn't have any other water in solution, the lead or tin acetate couldn't dissolve because there was no water for it to dissolve into. Although when we added the water to it, it should have theoretically dissolved, but very interesting. I'm not totally sure what compound we had, but something that was decomposing and releasing some sort of gas. Yeah, very, very bizarre. Nonetheless, I'm going to go put on a gas mask now, just because as it's decomposing and bubbling off that gas, it could be spewing up pieces of lead oxide, if this is lead oxide, which is very, very toxic. So yeah, I'll go do that. I'll continue what I'm doing and tell you what I do. It's very interesting what's happening. Okay, so we're going to try something a bit different here. Oh, by the way, just over in that solution over there, I've just struck a piece of zinc stripping there, and that should displace out any tin ions, if there is any in solution. And I just bought that tin metal from Home Hardware. You can buy it as zinc roofing strip in big long rolls. Anyhow, back over to here. So, after heating up our mixture there, and it was bubbling, releasing some sort of gas as it decomposed, I believe what happened is we had some lead or tin acetate, which wouldn't dissolve into the acetic acid solution, possibly, although it should have dissolved in the water. I don't quite get it, but I think we had an acetate which possibly reacted with, decomposed into the carbonate and carbon dioxide, which further decomposed into the oxide, because it's now looking a lot like lead oxide. Lead 2 oxide. Lead 4 oxide is black. Anyhow, but this is hopefully a mixture of a little bit of lead and mostly tin, because hopefully most of our lead actually went into solution based on what we saw over there. So hopefully this is mostly tin and possibly some discoloration from that rosin or whatever in the solder. I really don't know. It's just so weird to think about. But we're going to try to reduce it with some aluminum powder. This should form tin metal, and of course aluminum oxide, and anything that's left over, everything will be react with hydrochloric acid. The tin will react with the hydrochloric acid, forming stannous chloride, which can be electrolyzed, and then we'll form tin metal that way. So hopefully we'll be able to form some actual tin that way, but we're going to try it. So I'm going to mix our powder here with an equal amount of aluminum powder, which we ball milled ourselves in a previous video, and we'll just use a exact pretty much equal amount. It doesn't really matter because I don't know how pure this is or anything. I'm not weighing it out, and I'm not assuming that it's pure tin oxide. Anyhow, we'll just mix equal amounts, mix them up, and hopefully it'll burn. Okay, so this reaction could produce some toxic lead fumes or lead oxides in the air because it could possibly contain lead, but hopefully it doesn't. So we're going to set it on fire now, and hopefully this works. I just have a magnesium ribbon here, which will hopefully burn. And I'll back up. Definitely don't breathe in any fumes if this works. Should go any second now, if it's going to work, that is. Magnesium burns at 3,000 degrees Celsius, so it's definitely going to light it off if it was going to work, and it looks like it's working very well. It's burning with a good rate. Looks like it's produced, hopefully, some metallic tin. We'll let that cool down and we'll take a look. Okay, so that was a fantastic reaction, and I've just transferred the contents into this jar here. I'm actually out of large beakers, so we'll just use this jar instead. And I haven't washed any of them because they all contain lead salts and will need to be properly neutralized with sodium bicarbonate to produce that lead bicarbonate so we don't poison the planet and stuff. Anyhow, so now that we have this powder here, it hopefully contains some tin, and there's no large globs at all, but I could see a couple reflective pieces. And we don't want to go ahead and melt this so that it forms a glob, because we want it to be separated so that the lead doesn't react with the hydrochloric acid, if there's lead that was formed, but the tin does. Because the tin will react to form tin chloride, stannous chloride, which can be electrolyzed to form tin metal. So that's at least our hope. So I'll go ahead and add probably 150 mils or so of this hydrochloric acid here. And you can buy hydrochloric acid from places such as Canadian Tire. It's sold as muriatic acid, and it's 10 molar concentration. Anyhow, I'll add it in, then I'll meet you back. So I guess I didn't totally explain what's happening here. So we're dissolving any aluminum that's left over, any aluminum oxides that formed, any tin metal, any magnesium that didn't burn, any magnesium oxides, and hopefully not the lead. If we have lead oxides, then perhaps those will react, but they shouldn't. And lead chloride is insoluble in water anyhow. So whatever's left over should be lead salts and other impurities and stuff, which we can simply go ahead and filter off to be left with our solution of tin chloride, and as well as some other things. But electrolysis of this should give us tin metal. Nonetheless, this solution will need to be heated up, as tin does not react super easily at cold temperatures with hydrochloric acid. So we will heat this up. I'll probably go ahead and wash up my large beaker there and neutralize it and everything, and then go ahead and dump it into there and heat it up, so that hopefully everything reacts. Now, I also went and checked on that zinc strip, and no tin seems to be plating onto that, so it appears that we had no tin in solution, only lead in solution. But that's okay, hopefully we'll get some tin from here. Okay, so I've set up this little thing, and we'd filtered our solution after it had finished reacting, more or less. I mean, the bubbling just kind of stopped, there was still a bit of undissolved stuff, but hopefully that was lead compounds that didn't dissolve, or possibly some other impurities. Anyhow, it was filtered, and then we have a nice clear solution here, which is still strongly acidic. But this shouldn't matter, because I have two copper electrodes here which will not react with the hydrochloric acid, and are hopefully gonna make some tin metal when we electrolyze the solution, if indeed there is tin chloride in here. And then we can take that tin and melt it down. Anyhow, I'm going to be using a fairly high current, so I don't expect any pretty tin crystals, and they should just grow rapidly. Anyhow, I'll add it into this little dish here, and then I'll meet you back. Okay, so I'm just connecting the wire. 3, 2, 1. There we go. We'll see if anything happens. It appears that there is indeed a bit of bubbling occurring on this electrode over here. It is kind of hard to see, but that looks like tin that's precipitating out there. Oh, I'm pretty sure that's exactly what it is. Let's see if I can zoom in on that a bit. We'll see. Don't know if you could. My camera's now out of focus. That's no good. It's right there. You could see it growing. I don't know what it's trying to focus on. You can see the tin metal growing right there. It's very beautiful. It seems to be working. We're going to let this run for a bit longer and see how much tin we get. So, as you can see, we are appearing to grow a very beautiful little tree of lead over in the corner there. and it still doesn't want to focus. You can see it coming in and out of focus. I think it's trying to focus on the reflection or something. I don't know, but you can see that we definitely have a very, very beautiful little amount of lead there, or sorry, tin in the corner there. Okay, so we actually have some elemental tin here. So after growing that beautiful tin crystal, I went ahead and removed it, and I did end up growing a few more and melting them down. But I took the one nice crystal, which is really, really nice, and I put it in an ampule, and I filled it with mineral oil, and then I just epoxied it shut so that it couldn't escape. And I put it in mineral oil because it's super delicate, and you can just see how beautiful the crystal is right there. You can see all those beautiful little spikes of tin metal that were grown out from that electrode. Anyhow, it's quite a beautiful crystal, and I'm quite happy with it. So that's certainly going into my element collection. I also have these two little beads of tin, which were produced by taking one of the crystals and melting it down. So you can see those two little beads they're not very big, but it certainly is a fair bit of tin right there. Anyhow, so that's basically my element sample for tin. And then here's all of the lead bicarbonate, which we recovered by filtering out the solution, which contained all the lead bicarbonate. And that's a majority of the lead. Whatever lead was left was lead bicarbonate's really, really insoluble, so it's not going to be an issue in terms of being absorbed by your skin or anything. So make sure to convert to lead bicarbonate, all your waste. And then, of course, we still were left over with a bit of this tin oxide compound, I believe. Whatever this might be, we were kind of confused at what it might be. But when you heat this up, it decomposes, and when you take whatever it decomposes into, it reacts with aluminum to form the tin, which we then dissolved in the hydrochloric acid to form the tin chloride, which we produce this tin from. Anyhow, this is basically how to make tin from household materials, and how to extract it from solder. Now, that took a lot of chemicals and a lot of work, but tin could be useful in future applications, and I'll probably go ahead and produce a bunch more tin and melt it into little beads like this. I'll just take a whole, probably roll of solder and just dissolve the whole thing. You could probably be much more efficient with your uses of nitric acid and concentrated acetic acid. However, this was just a first attempt I've ever done, and I've never seen anyone else actually extract tin and lead from solder, so that was very, very fun. Anyhow, I hope you guys enjoyed, and I'll see you in a future video. Oh wait, bye.